short and heavy? Mr. Harris, Jeff Harris. Yeah. Yeah. He does developmental math, so you probably didn't have any classes on them, did you? Yeah. That's who I'm guessing is. Real nice guy. Okay. All right. Only because I have to say it will I say it. But this class, perfect. All three of you are paid. Way to go. But I have to say it today. The Vice President said we did. That, any students who haven't paid by Wednesday are going to be removed from the roll. So if you still know of anyone here at the college who may not have completed payment, tell them they got to get it done today, tomorrow, no later than the end of business on Wednesday. Okay? I'm supposed to read a little script, but I forgot to print it out, so that'll do for it, hopefully. All right, I think we did this slide last time, didn't we? Example 4. I have my mark on example 4. You can't see that? What's wrong with you? Put on glasses, huh? Oh, man. Okay. All right. Yeah, that's what I had. And we're starting at example 5. Yeah, I remember doing that one. So, that's what it was. They didn't have example 5 on the slide set. So I probably shouldn't have even done this one. So let's do it here. Find the area of the region that is bounded by the 3 curves. Let's see if I can get. All right. Let me get my pen set up. Okay. Going to do the graph up here. Okay. By the 3 curves, y is equal to x squared. Okay, let's just 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Oh, one decided to show up today. Isn't this nice? He likes coming to school on Mondays, huh? Okay. What's that? Oh, I'm sorry. Can you sit back there? No. Okay, no, I'm just kidding. I knew I'd seen it before, but I was at the UAB game on football game on Saturday. Donna, who is a big supporter, they were on the screen several times. I was looking for your picture, but I never saw it. Oh, really? Oh, baseball players are such. No, okay.
So UAB coaches, they actually get to use brand new trucks from us.
Oh, wow.
And once they get up to 5,000 miles, then they come back and get a new one.
Wow. My wife works at UAB. Can we get something? No, I'm just kidding. Okay. Okay. We're doing example 5, top of page 337. Okay. The first curve is y is equal to x squared. Okay. Can you give me a few points on y is equal to x squared? 0, 0. 1, 1. Points are ordered pairs, by the way. Negative 1, 1. That's good. 2, 4. Negative 2, 4, and the rest are off scale. So there is our parabola, approximately. I don't draw very good parabolas. Okay. So find the area of the region that is bounded by that curve. Y is equal to, okay, this is y is equal to x squared. Now, the second curve is y is equal to x minus 2 squared. How do I plot that one? Second? Okay, give me a point.
Would it be the same thing, but just shift it over to the right?
Okay, very good. How far?
2.
2. Okay, yeah, shift 2 to the right. So shift 0, 0, 2 to the right. Shift negative 1, 1, 2 to the right. It'll be right there. You want me to do this on a different color? They did red, so let's do red. Okay. And shifting this one over 2 to the right is here. Shifting this over to the right is there. This one 2 to the right would be there. So here is the second parabola. Again, very poorly drawn. Okay? And y is equal to 0. Well, y is equal to 0 is the x-axis. So let me go back to, well, let's go to this color. Okay? All right. So the area defined by those 3 curves is this area right in here. Got it? Okay. Let me go back to black then. Oops, that's not what I meant to do. It's not black, it's dark though. Okay. Find the area of the region bounded by the 3 curves. All right. I can think of 2 ways to find the area. You tell me what you think. Under what? Under this one? Okay. Okay, now, according to my ugly looking graph here, it looks like they may be intersecting at 1, 1. We probably need to confirm that. How do we confirm they are going to intersect at 1, 1? Second? You could do that. Let's see what happens if we plug in 1. 1 there will give us 1, and 1 there will give us 1. Okay, yeah, so that's one. The other way is set them equal to each other. That would have worked too, but that's a good way. If you have a guess. If you didn't have a guess, then you need to set them equal to each other. But it was a pretty good guess. Okay? So, let's go back to Bailey's suggestion. What were you saying to do? Under this one, and then add it to the area from 1 to 2 in the back. Is that what you're saying? That sounds like a possible winner. So, what do we have? So, one thing to do is decide what D's are you taking. You know what I'm talking about? The way I understood you say we're going to take DX's, right? And do the area that way, right? Is that what you meant? Okay. So that would be then your, and that's while we were saying, I was saying from 0 to 1, because that's changing on X. So this would be from 0 to 1 of what? X squared. Second? Plus? Okay. I'm going to do the plus here because you can't do it the second integral. That's the second area. What's your second? dx. That's what I say. We're taking a dx here, right? That's what you need to identify. See, the book's doing it differently. No, they're not. They're doing it right. Okay, good for them. Okay, plus. Now you plus. Second, x minus 2 squared. Okay, I'll buy that.
dx. 1 to 2. Okay, very good. Tag team here, okay. Now, this one is not too hard to do. What would that be? Second. You probably said it right. Are we taking an antiderivative or a derivative? Oh, okay, x to the third. I misunderstood. X to the third over? I thought so. Okay. And this is going from 0 to 1. I can almost do that one by myself, but I'll use your help. Okay, this one, how do you want to do that? I can think of at least 2 different ways. But you think of your way. How would you do that?
Just leave the thing in parentheses like it is. They just work around it.
Okay, what do you mean by that?
So that would be x minus 2 cubed over 3.
X minus 2 cubed over 3. That is a perfectly good way to do it. Basically, you're doing a substitution without doing the substitution. You're keeping that entity by itself. Not bad, okay? And you're evaluating that from 1 to 2. Okay, can I get a little help on the first one? 1/3. Oh, very good, okay. Okay, now it's your turn. No. All right, what would be this one then? Okay, say that again. -1/3? Is that what you said? How did you get that? Okay, you first put a 2 in there and you get 0. Okay, I thought you were sticking that stuff. Okay, good. Now, then you do a minus, because you're doing the lower here, right? Minus plugging that in. Where if you plug this in, you get a -1 cubed is -1. So that would be a -1/3, but you have a minus because it's the lower limit, right? So that would be a plus, okay? You see that? Okay. So that gives you really hard math. 2/3. Very good. All right. All right. That's what they got to. Good for them. Now, they wanted to redo the problem with a horizontal because the region is horizontally simple. Sure it is. But why would you want to go through that mess? Okay? This was such easy integrals to do, especially with your clever insight, and just keep that as a unit and do that worked really well. Okay? But if you did it be wise, because it is horizontally simple, then you have to this leg minus this leg. Well, then you have to get that in terms of y. Well, that would be x minus 2 is equal to plus or minus the square root of y, right? Square root of both sides. And you're on the minus side, so you would use the minus square root of y. So it would be x equal 2 minus square root of y. That would be this one, and this one would just be x equals square root of y, the plus side of this one. So it would be the difference between those two. You would still get the same answer, but man, it seems like much more opportunity to make an error. I usually like to avoid those, okay? But to do it the other way, it would be this time, if you're doing your dy's, then your dy is only going from 0 to 1. That's a little easier. I don't know why that moved. Okay? You're doing the dy. And then what is your y? You're doing your things this way. This one was root y is equal to x minus 2, right? But it has a plus or minus here. This is the plus side, that's the minus side, right? So we're taking from this side, so you're using the minus. So x is equal to, add 2 to both sides. So x is equal to 2 minus root y, okay? And over here, you're doing x is equal to plus or minus root y again, but now you're doing from the plus side of it, but you're subtracting it, so that would be 2 minus root y minus root y, okay? You see that? So this would be the integral from 0 to 1 of 2 minus 2. I don't like to integrate root y's. How would you suggest I do it? To the 1/2, y to the 1/2. So let's just leave that parentheses out of there. It's not doing us any good. Okay. Okay, what does that give you? Okay. Okay. Say again? Antiderivative of 2 dy. Say again? I can't hear. Okay, so you want to do integral from 0 to 1 of 2 dy minus the integral from 0 to 1 of 2. Let's pull this 2 out here. In fact, we could have pulled the other 2 out there too. Okay, what would that give you? Okay, 2y, right? Okay, 2y evaluated from 0 to 1 minus 2 times I'm going to guess a y to the second. I don't think so. Huh? 3/2. Add 1 to it. 2/2. Okay. Okay. But then you have to multiply by second 2 over 3. Right. Oh yeah. I thought you said that. Okay. All right. And that's evaluated from 0 to 1. Okay. How about that first one? That's sort of hard. 2, good, minus. I'm just going to pull the 4/3 out. Okay. 2 times 2 is 4. Okay. And then evaluate y. What would that be? Huh? 1. Exactly. Y to the 3/2. Evaluated 1 is 1, evaluated 0 is 0. So this is, how many thirds is 2? 6/3 minus 4/3 is 2/3. Hey, same answer. So either way would have worked.
To me, the calculus is harder that way. I thought the way you did it the first way is the simple way to see it. Even though you have 2 pieces, you still, on this one, you do 2 integrals, so they're just the same limit. You could have done that as 1 integral if you wanted to, but still, it's a lot messier, fractional exponents and that kind of stuff. So
I like the way you did it first. But both answers, both ways, approaches give you the same. All right, there is a summary there. Certainly welcome to look at that. Do you find the preliminary questions worthwhile to do? No? Yes? What? Huh? Okay. Someone give me an answer. You want to do preliminary questions or not? Move on? Okay. All right. Homework exercises here then, but if you want to see them, I'll be glad to do them. Okay. All right. Do either 1 or 3 or both. Do number 5. Do number 7. Do either 9 or 11 or both. Do either 13 or 15 or both. Either 17 or 19 or both. Do 21. Do either 23 or 25 or both. Do 27. Do 29. And then do any of the odds, 31 to 47. 49 says you need a computer algebra system. You can try it without it. I think you can probably do it, but if you can't, don't get too bogged down with it. Okay? 51 is is sort of a think-through type problem, so it's not bad to look at that one. Then do either 53 or 55 or both. 57 says you need the computer algebra system. If you can do it without it, try it, but it probably would be easier with something, so you don't have to do it if you don't want to. Do 59, and it has a figure up there you can look at. And then do 61. Well, 61 is sort of a think-through type problem. But one thing to notice about 61 is that it's talking about a Gini index. Now, that's not, I dream of Gini, don't get going there. This is a GINI index. So that leads me to think, who in the world is Gini anyway that came up with this index? How did Gini come up with the index? And what is the index used for? That kind of stuff. You could get a couple of paper topics off of that one. And actually, they talk about it in 61 and 62. So even if you don't do 61, you might get a paper topic out of it if you haven't done one already. Let's see. That's one of my most advanced classes. How many papers have been turned in? Oh, none. Okay. So let's move on to 6.2. Any questions on 6.1 before we leave it? Okay. So let's move on to 6.2. Sorry, it's taking a while to load. There we go. All right. Here's a little generic stuff at the beginning. Later we'll get into more specific. If you remember from, no, I'm sorry, that was another class. This is a right circular cylinder. No, a right cylinder. Not a circular cylinder, that's a tin can, right? This is not a circular cylinder. It has some base. It looks like a footprint or something like that, right? But not quite. You have a bunion over here. Okay. But it looks like a base raised to some height, and because it's vertically from the base, that makes it a right cylinder. A cylinder, by the way, is any curve that extends infinitely high and low. This is an infinite, but it is a cylinder. It's a portion of right there. This curve happens to be a closed curve, so you have a closed cylinder. A cylinder doesn't have to be closed. You'll learn this in Cal 3. But what the
volume of that cylinder is whatever the area of that base is, whatever that is, times the height of the cylinder. That is generally your volume, base times height. Okay? Now, why are we using that? Well, let's look at a problem here. That is a rather bizarre looking shape. What would be the volume of that shape? Well, now this isn't a cylinder at all. Okay? It's big at the bottom, gets thinner, and then it looks like it's going to get bigger again. So that doesn't make a very good cylinder. However, since it's shaped and sitting on, say, the XZ plane, though we don't show Z in here, sitting parallel to that and going up in Y, if we take our dy's here, between y's of I minus 1 and y's of I, then this shape here, even though it's not a cylinder, that's the small enough variation there, you can approximate that with a delta y as a height and treat that as a cylinder of either this base or that base. It doesn't matter, they're probably going to do the top base. It won't be exact, but it'll be pretty close. Okay? Now, how do you get it closer? Yes, decrease your dy. The smaller that is, the closer that is to being an exact cylinder. It's not ever, because it has some curve there, but you're getting closer and closer, so you take the limit of that, and you would get, well, then you sum all these cylindrical shells, not shells, slices, okay, and you've got approximately the base of the volume of the whole container, okay? So we'll just say that the area of this slice happens to be some function of y. Now they use the y I minus 1. I thought we were going to use y sub I. It doesn't matter which you use, this base or that base, either base. You let it get smaller, they're going to get close to each other anyway. But that's the cross section A. So you have to figure out an expression in y for that area. And then you're summing on your dy's or delta y's from A to B, because that's where your shape is in between those two. And there you've got the volume. So divide the solid into thin horizontal slices. Each slice is nearly a right cylinder, whose volume can be approximated as this area times its height, and its height is the delta y. Okay? Guess what? When you do that and take a limit, that becomes a dy, and whatever that area function is, that's what you're going to take over y A to B. So, this is what I was just saying, expressed in beautiful little mathematical terms. The volume has an integral of a cross-sectional area. Let A of y be the area of any horizontal cross-section at height y, okay, of a solid body extending from y is equal to A to y is equal to B, just like from the last picture. And the volume of that solid body would be the integral from A to B, y going from A to B of that cross-sectional area A of y. Okay? That is the limit of all those little Riemann sums of the incremental slices. Okay. So what turns out being the issue here is not the integration, it's finding the area. That is the hard part. The integration, once you find that area, then it's easy to take the thing. So it's interesting how they name this section. Setting up integrals for volume density and average value. Really, the setting up is sometimes harder than the integration. Okay? And it's not super hard, but sometimes it takes more effort. I think this is example 1. Okay. I'll blow it up for us to take a look at it, but to do any writing, we're going to have to reduce it back. So here's what we've got. Calculate the volume V
of a pyramid of height 12 meters, so that y, y, that they have going from 0 to 12, and those are in meters. So that is a very tall pyramid. That's about 4 stories, okay, approximately. Pyramid of height 12 meters, whose base is a square of side 4 meters. So this is 4 meters here, 4 meters here, 4 meters there, 4 meters there. Square of 4 meters. And they say a pyramid, this is a right square pyramid. Okay? They didn't say that, but that's what your assumption is here. All right. Now, I hope it's fairly obvious we're going to want to take our dy's, since we're letting y be the vertical axis here. And they don't really show your coordinate axes here well at all. They kind of infer that's the x-axis, so they don't label it. And the y-axis going there, but they sort of label it there. Okay? Now, you're going to do dy's here, so that's a representative slice here, dy. What you have to do is get the area of that slice. Okay? I hope you see that's going to be a square. Okay? What you've got to figure out is what's the side of that square. And things you don't know are usually pretty good things to name as a variable. Right? So let's let S be the length of any one of those sides of that square up here. Now we need to get that S in terms of y's. Let's see what we can do with that. Okay. Part of this was the judicious placing of the y-axis here. It's right at the center of that square base, going through the vertex C. Okay. So our y is going from 0 to 12. We know that right off the top. Okay? Why is it going from 0 to 12? So we need to know what this side of this base, side of this, we know this one down here is 4. What is this S here? And by the way, this representative section is y above the x-axis. So that height is going to be y. Okay. Which leaves this height up here to be 12 minus y, right? Total height is 12. You're going from 0 to y here. Okay, now the length we said we were going to name each of those sides S. Okay, so that square that's in there has an area of S squared, but we're not really interested in that yet. Okay, what we are interested in is this triangle right here. Okay. Again, you chose judiciously to have the x-axis going right through the center of the square, parallel to these sides, okay, right through the center. So that means if this base is 4, that's a length of 2 here. That's a length of 12 up here. So 2 is the 12, and if this length is S, this is also 1/2 S, just like 2 is 1/2 4. So this is 1/2 S here. So 2 is to 12 as 1/2 S is to 12 minus y. Similar triangles. Okay? This expression that we just said there, let's write down that ratio. I've got to shrink it. Okay? I've got to change my color. Okay. Now I'm ready to go. 2 is to 12 as S over 2 is to 12 minus y. Did you buy that? You look for things like similar triangles here. 2 is to 12. This length here is to that height there, as 1/2 S is here, since that side is S. 1/2 is S is to 12 minus Y. Right? Okay. Now, how do you deal with a proportion? Cross multiply. Okay, this will be 24 minus 2y is equal to, when you multiply these two together, there'll be 6s. All we're interested in is s, right? So s, let's first divide everything by 2, like this. So 3s is equal to 12 minus y. So s is equal to 4 minus y over 3. Do you buy that? Divide both sides by that. So this gives you your s as a function of y. There you have it. Okay? Now you know the area of that square here. It's this thing squared. Messy, but doable. So your s squared, that's the area of that thing, is equal to 4 minus y over 3 squared. Well, let's multiply that out because it looks like such a fun expression. What would that be? 16 plus second y squared over 9. Is that what you muttered? I mean said? Is that right? Or are you bothered by the fact there's a big gap in there? What goes in that big gap? Twice the product of those two. Right? Minus 8/3 y. If you don't believe me, take yourself to the side and pull it. Right? First things first, it would be 16, and then you have a 4 times this, plus another, this times 4, right? So it's twice that product. Got it? Divide. Okay. Plus y squared over 9. So that's our area of that slice in as a function of y. That's your a of y for this thing right here, because that was s squared and we just did that. And then we can do it, can't we? What would be your integral? The volume will be the integral from 0 to 12. I'll buy that. (16) minus 8/3 y plus y squared over 9 dy. That should do it for us. So what we got left to do is do the integration. Antiderivative of 16 dy. 16y. So that would be 16y minus
Would it be 8y squared over
8/3 y squared over 2. Is that what you said? I thought that was. Okay. And 8 over 2 is 4. So it would be 4/3 y squared. All right. Yeah. Very good. Okay. And plus, second. Okay. All right. We had the 8/3 there.
write it what it said. And then you had a y squared over 2, right? Okay. Well, y squared over 2, the 2 will go into 8 4 times. So it's 4 y squared. Okay? I'm sorry, I skipped a lot of steps because I have a lot of room to write. And I'd like to confuse you as much as possible. That's my job. They pay me extra if I really confuse you. Okay?
All right. Next. Y to the third over 27. All right. Evaluated from. Okay. I think it's time for a calculator, don't you? I can almost do 16 by 12, but I'd rather not. You do it. — 12 by 12 is 144, and 4 by 12 is 48, so that'd be 192, I'm guessing. 16 times 12. Or are you doing the whole thing? Okay. 64? Your whole answer. Okay. I should have been doing it in my head to see if I could beat you, but let's see. 64 cubic meters. That's exactly the right answer. Okay. Very good. All right. Yeah, the integration had some issues, but really the key thing was getting set up that area of that slice as a function of y. And you use your similar triangles to do that. Does that make sense? Okay. Any questions on it? Okay. All right, that was example 1. Let's see about example 2.
Will all these type problems have a picture to go off of?
No. I thought you were joking. Okay. That's the key. Generally, you have to draw your pictures. So, maybe the first step in it is getting the drawing right and then figuring out the thing. Yeah, you got all that to do in general. Okay. So it takes some pretty careful reading. Let's see if we can read this one and get it to make sense here. Compute the volume V of the solid in figure 4, okay, whose base is the region between the inverted parabola y is equal to 4 minus x squared. Now, looking at just the base now, there's your x-axis, there's the y-axis, laid down like this, and y is equal to 4 minus x squared. That would be a parabola. Minus x squared, y is equal to minus x squared would be like this, right? Then you elevate that 4 units up, so that's what you got. Okay? Now, the base, and this looks like some sort of a Quonset hut or something like this, maybe some type of a tent that you cut in this shape, and you're going from the x-axis back. That's going to be your shape there. Well, it looks like we've got to pretty much do dy's, don't we? That's usually a good thing to start with. What is going to be your increment? Looks like it's got to be a dy. Well, if that's a dy, then that's your thickness here. You need to get the area of that semicircle that you get from rotating that parabola around half the time. That's the semicircle. Now you got to get your radius to get the area of that circle. So you need to know if this is y, how far above the x-axis you are, that's your y, then what is that radius in terms of y? Well, it's some x, and you That's what you got to get in terms of y. Okay. So basically, what we're looking at, go up here, some measure y, figure out what your x is that corresponds to that. We know that y is equal to 4 minus x squared. Okay. But you're wanting x as a function of y, right? Because you've got to have a dy here. So you've got to have your x as a function of y. So you have to solve this for x. They did, I think, way too much for you here. Solve this for x. Because you want this as a function of y. Here you got y as a function of x. You need x as a function of this y. Okay? So it's not a hard thing to do. How do you solve this for x? I've got to shrink it. What would be the first step there? Okay. And what would that give you? Y minus 4 equal negative x squared. Okay, I'll buy that. What's next? Second? And what will that give you then? 4 minus y, very good, is equal to x squared. Second? Take a square root. So you get x is equal to the square root of 4 minus y. Now, technically, when you take the square root of both sides of an equation, you should do a plus or minus square root, right? And this would be the plus, that would be the minus. But guess what you're looking for? You're looking for a radius that you're going to flip across like this. I don't like radii to be negative, so I'm not going to use the negative. I'm only going to use the positive. I'll use this side and rotate it around that way. The radius is still, wherever it is on that semicircle, is still of positive length. So we'll use that. So x is equal to the square root of 4 minus y. Okay? Now, that gives you a radius. You're dealing with the area of a semicircle. What is the area of a semicircle? It's the area of a circle. Okay? Over 2. So you got pi r squared over 2. That's the area of a semicircle of radius, but the radius is the square root of 4 minus y. But when you square the square root of 4 minus y, what do you get? 4 minus y. You got pi over, say pi and write 4. Something's wrong with the brain here, okay? Okay. Pi over 2 times 4 minus y. So that is your area as a function of y, right? What do we do with that? Say again? Okay, and how do we integrate it? What do we integrate? Integral from 0 to 4, because you're integrating along y, dy. That was your first thing you determined there. This is your dy, okay? Pull the pi over 2 outside, right? It's just a constant. Why not? Okay? And what do you have left then? 4 minus y dy. I think maybe we can integrate that, huh? Okay, say this again now. You could do that perhaps, but why don't we just integrate 4? What would that be? 4y. Okay. Now, here's why I hesitated going along with you on the other one. I mean, could do it, but then you've got a chain rule type thing going on in there, you know, undo a chain rule and stuff. It just is a little more problem than it's worth, I think. This is so straightforward here. What does that give you? I'll do the pi halves part. Okay. What will this be? 16 minus again? 32. This isn't smelling too good, is it? What have we messed up here? No? Oh, reading my writing is what we messed up. Okay. I was reading that as a 3. It's not a 3, that's a 2. Okay. I don't know if you're reading it as a 3 or not. That's a 2. The pen sometimes right. What does that give you?
16 pushes 4.
Say again? How did you get that? All right, so more like 8. Okay. And that would be 8 times pi halves, which would be
8 pi halves, 3, 4 pi halves.
okay, one more time. 4 pi. Split the difference. Okay. 4 pi. All right. Let's see what they got. Oh, look at that. They got it right, too. Good for them. Okay. Colts can sometimes do that to your head, can't they? All right. Make sense? All right. That one really started out being like, this could be awful. But the integration turned out being far easier than the last one, which was a lot more straightforward looking problem. So you can't always tell. Okay. Any questions on those? All right, let's do this one. The volume of a cylinder, and we're going to get this with a vertical cross section. Compute the volume of a cylinder of radius r. Well, here they've drawn it for us. Volume of the cylinder and the radius is r. So that means if you put the center of the cylinder, sphere, why am I saying cylinder? Volume of a sphere, yeah. Okay? If you put the center of the sphere at origin, then this is going out plus r here, plus r up here, minus r here, right? Okay. Now, you could have chosen any cross section. They chose a vertical cross section. Okay? So they're going to look at here. When you do it this way, what do you notice right off the top? dx. You're doing a dx. So by choosing this, you have this to be a d. Oh, I forgot. This is going to be a dx. Okay? Now, where is the x running from and to? Okay. I like that as long as you notice something else. 0 to r is a hemisphere. Okay? So if you're doing 0 to r, realizing that back here is exactly the same, you're going to double that integral that's going 0 to r. Or you could have gone minus r to r and done the whole story, the whole thing. I like the idea of doubling from 0 to r. Is that what you were thinking? Of course it was. Yes, of course. Okay, good. You see what we're saying? Okay. So we've got the dx here and the x going from 0 to r, and we're going to double the integral. Okay? Buy that? Okay. Now, what we have to do next is find the area of that circle, because a slice of a sphere is going to be a circle. The circles are getting smaller. So, goodness gracious, how are we going to find the area of that circle there? Second? Pi r squared is going to be important. What is your r in that case? Okay, how did you get that? You read it off the board. Okay, good for you. Okay, we're having to think of this. You drawing the problem from scratch. How do you figure that? Well, let's take a look at it. You know this distance here is x, right? From 0 to r. Your distance here on the x-axis is going to be x. Okay? Now you know that the distance from the center to any point on that circle is going to be capital R, because it's a circle of radius r. Right? So what we have here is x. What we need is that radius there. The radius here is your y value. Right? And the y here, if this length is y, and this one's x, that one's r, and this is a right angle, right angle, but rectangle means right angle, okay? He's talking Greek to me, okay? That's a right angle, and what can you tell me about the relationship between the x, the r, and the y? Say it. Say it. Yes, and what's your A, your B, and your C? X squared plus, let's call it y. Y squared. C squared. Okay. So we want to figure out what that y is. Okay. So y squared is equal to r squared minus x squared, right? And that's where you get it, because the square root of y squared would be the square root of r squared minus x squared, right? And we're only going to take the positive. We're not going to worry about plus or minus, because we're going to take a radius being positive. And that will now be the radius of that circle. And what's the area of that circle? And that's your radius r that we're talking about, the little r here. So your area of this circle as a function of y would be, no, as a function of x, sorry about that, we're taking a dx. So we want this as a function of x. And what would that be? Pi r squared minus x squared, because it's radius squared, that's the square root, so you get that. All right, I think we're ready to go then. What's our integral? What's our volume? Let's say it this way. 0 to r, is that what you're saying? What else? Pull out a pi. I like pies, okay? R squared minus x squared. Dx. Is that it? Okay, not quite. 0 to x, 0 to r. Okay, either you put negative r there or you put a 2 in front. Okay. That's why I was afraid by doing that you'd forget to put your 2. And you did. Never mind. Okay. So, let's go from there. This will be 2 pi antiderivative of r squared. Say that again. Okay, wait a minute. R is a constant. That's your radius. X is the variable. Okay? So that's R squared X. Right? Minus X cubed over 3, evaluated from 0 to R. Okay, so we've got 2 pi, and you plug in capital R for X there. What do you get? R cubed minus over 3. I'll do the 0 part. Okay, done. Okay, and what does that give you? How many thirds is R cubed? 3/3. So this is 3/3 R cubed minus 1/3 R cubed would be 2/3 R cubed. And when you multiply that by 2 pi, what do you get? You don't need a calculator. 2 times 2. 4/3 pi R cubed. Didn't we know that already? You go to the bottom of the inside, the one page over from the inside cover, there's your volume of the sphere, 4/3 pi R cubed. Very good, we knew that already, didn't we? Flip back one. Yeah. See it? All right. Makes sense? Verified, we got it right. 4/3 pi R cubed. And they got it right in the book too, good for them. Okay. When you do take the shortcut to do only half of it, be sure you double the integral. Okay. Got it? All right. There is a little blurb at the top of the page called a conceptual insight. I don't know exactly how to pronounce this guy's name. I think it's Cavalier's principle or something like that. I think he was an Italian, sounds like it anyway, mathematician, and he came up with this principle that solids of equal cross-section areas have equal volumes even if they're tilted or something else is happening, because, and this is the example here, our dy's would be the thickness of these coins, and it doesn't matter how you stack them or lean them or anything else, the volume is still the volume is the volume of those coins, right? And that's that two-stack. Blow this up a little bit. So if you have equal cross-sectional areas, it doesn't matter what kind of weird shape that you have. I've been to New York City once, and there's some building there that some architect decided to make really bizarre. And it's not straight up and down building. It has all these weirdnesses to it. But I think he has equal cross-sectional areas, so it works. Why he chose to do, and it's a pretty tall, 9, 10 stories or something like that. Pretty tall building. It's ugly as everything, but you know why he chose to do it. But he did it. But Cavalier's principle says it doesn't matter. But the equal cross-sectional area. I'm not sure he has to equal, but I think it looked like it would be, and they have equal volumes. Okay. Just a little blurb. We're not doing anything with that. Okay, but there's a potential paper topic or two. Who in the world is Cavalieri, or whatever his name is? And how did he develop this? Or what's the application of it, maybe, if you can find one. Okay, almost think leaning tower of Pisa might work. It might, you know. Okay, now we're moving into density. And here is a truth about density. The total mass of anything. Right now, we're talking about a rod, a wire, or something like that that has linear mass density. Whatever your density is, if it's a linear mass density, how much say kilograms per foot or something like that, pounds per foot, something like that. Pounds is not mass, so if you're given a density in linear terms, then the linear mass density times the length will give you the total mass of the object. Now, I'm trying to remember. I don't like the fact they use rho here, because usually I think of rho as being a body mass density. They're using it as linear. But as long as you understand that, then the linear mass density times the length would be the total mass. Now that's assuming a constant linear mass density. And of course multiply that by. Now it gets interesting when you have a variable mass density. So we'll get there later. So following, and by the way, I don't think I said this earlier. One reason I'm hoarse is I went to the game Saturday, so sorry. Just wait till I go to one of the baseball games. You'll have to listen to it, but that won't be this year. Okay. All right. The total mass of a rod is equal to the area under the graph of the mass density. See, here we have a mass density that varies with length. It's not a constant density. This is varying with length. So what you do, you split this into dx's here, and then you do rho of x dx to give you the mass density of each of the slices, and then add those together, which is the summation, which is your integral. And you integrate dx times rho of x, and that gives you your density. Okay. Now, they go back to Riemann sum type ideas by picking some point in that and calculating the density at that point, and saying that's approximating what it is for the whole delta x. And as long as you get the delta x small enough, that's a good approximation. So the density is the rho as a function of x times the delta x, which when you integrate rho of x dx. Okay, so if you knew that function rho of x, just integrate it from a to b. Make sense? All right. So here is your integral based on what we just said. The total mass m is the integral from a to b of rho of x dx for that illustration we just had. This is if you have a variable linear density for that rod, wire, pipe, whatever it happened to be. So I think we're ready for example 4, but I don't think example 4 has a figure, does it? No, I don't think it does. That's the figure for the next one. So we'll have to do our own. Find the total mass, M, capital M, of a 2-meter rod okay, 2-meter rod of linear density rho of x is equal to 1 plus x times 2 minus x. And that will be in kilogram per meter. Linear mass density, mass per unit length, where x is the distance from one end of the rod. So we'll let x be increasing going this way. Okay? How would you propose we find the total mass of that rod? Second? 2 times 0 is ours. I didn't hear. Okay, except, oh, okay, I see what you're saying. If this were a constant, that would do it for us. It is a constant, it's a variable mass density. At length, when x equals 0, your mass density is 1. Okay? When x is equal to 2, your mass density is also 1. Okay? But when it's 1, your mass density is 1 plus 1 times 2 minus 1 is 1. That would be 2. So actually your density is going from 1 to 2 to 1 again. So it's not constant. It's varying. So we do that. But before I would do that, I would clean up that mass density function a little bit. Let's multiply it out. Distribute the x across parentheses. What do you have? 1 plus 2x minus x squared. That's going to be far easier to integrate than that thing. Okay? Unless maybe you have a way to integrate that one as a thing. That's not. So your mass is the integral from, the way I drew it, you're going from 0 to 2 of this mass density, 1 plus 2x minus x squared dx, because we're going to take our dx's this way. Right? Can you do that integration? X squared minus x cubed over 3. And integrate that from 0 to 2. And that would be okay, 2 plus 4 minus 8/3. So this would be 6 minus 8/3. How many thirds is 6? 18/3 minus 8/3 is 10/3. 10/3 kilograms. Because we're looking for total mass, and it was mass kilogram per meter. Okay? Let's see how they did. There, they got it right. Good for them. Okay? Now, in some situations, density is not a function of length, but of distance from a center. So let's say you had a sphere here that the further out you got, say the less dense it got or the more dense it got. So you have what they call a radial density. That's what they're talking about here, a radial density function. For instance, in studies of urban populations, it might be assumed that the population density, rho of R, in people per square kilometer depends on the distance you are from the center of the city. Now, this is changing these days, by the way. I don't know if you've noticed it or not. I think when cities first formed, your population was near the center, and the further out you got, the less dense it got. But then came cars, interstates, things like this, and now people started moving out of the cities and commuting in. So your population density would start low at the city center and do whatever it's going to do, and then somewhere out there it starts getting bigger. Nowadays, though, with gas prices going up, and especially you smart millennials say, why drive this long? Why spend my time driving, paying for gas when I can live in town near my work and then have more free time? Because millennials are lazy. No, I didn't say that, did I? Okay, so now I think you have people moving back into city centers, so your population density is going up. It probably still got some suburb stuff like that going, but it's a different function. But you see, it's a varying function. It's not constant. It's not that everybody lives the same distance, from the city center. Okay, so that's a radial density function, and this is an illustration of that. We may now derive a formula for a total population P within a radius capital R of the city center, assuming a radial density function, rho as a function of R, where R is the distance from the city center. First, divide the circle into, of radius capital R, into these circular rings. I guess most rings are circular, okay? In thin rings with the width of the thickness of the ring being delta R, because you're going from 0 to capital R over that, okay? And if you had n rings, like 1, 2, 3, 4, 5, 6 rings, then each of the little delta R's would be 1/6 of your capital R, okay? So the ring of width delta R. So what is the area of that ring there? Well, here's one way to think of it. Imagine, this is not very fair, but imagine you take that, let's say we cut it right here, and then stretch this out and make a straight line with it, make it into one long thing. Its thickness would be delta R, the width would be delta R, and its length would be, what do we call that? Surrounding circle. Second? Circumference of the circle of radius little r. Okay? I think they call it little ri. And the circumference of the circle of radius ri would be 2 pi ri times delta r. So that would be the area inside that ring. Okay? And then so what you would need then is a density function that's not a linear density function, but an area density function. Because that's what you're talking about, the area within a certain thing. And so, let's see if they show that for, yeah, here would be it. Get my thing to operate properly. So the population within a radius capital R of an area would then be the 2 pi came from the circumference, right? 2 pi R times the rho of R. The rho of R is now not a linear density, but an area density. Density per unit area. Why per unit area? Because R is the area, is the length measurement. DR is the length measurement, so this is length squared, which would be area. Okay? And you're going from 0 to capital R, from the center out there. So here's your population within a fixed radius. And I believe example 5 is going to build from that, but it don't have a figure for 5, so let's just do it. The population in a certain city has a radial density function, rho of R, is equal to 15 times 1 plus R squared to the minus 1/2. Okay? What a lovely little density function, where R is the distance from the city center in kilometers, and rho has units of thousands per square kilometer. How many people live in the ring between 10 and 30 kilometers from the city center? So what would be your, how would you do that? So, how would you do that? Okay, this thing right here goes in for the rho, right? Okay, so what can we do? What would your integral look like? The population P is equal to 2 pi. Second? Okay, I'm looking ahead a little bit, and notice that 15 is just sticking out there without anything multiplied about it or anything. So why don't we make that 30R? 2 times 15. Would you be okay with that? Okay. I'm just real lazy that way. 30 pi times the integral from what? Really? What's our problem here? How many people live in the ring between 10 and 30 kilometers from the city center? It's 10 to 30, yeah. See, this is a slightly different problem from that one, okay? And then we have okay, don't forget the R. R, that sounds like a pirate joke, doesn't it? Never mind. And your rho of R, since you've already pulled out the 15, would be 1 plus R squared to the minus 1/2. And then dr. R. How would you do that? I'll take care of the 30 pi. Okay. How would you go from there?
Would be RX.
Say again?
RX.
Rx?
Is it 2 dx or dy?
It's dr.
So the R squared.
Say this again. Okay, that's part of your answer here. I would. How do you integrate that? I mean, in case it's bothering you, get this off the way. That's what I'm trying to integrate. What's that? No, that's, even though it's written differently, that's your variable R. That's an R, that's an R, and that's an R. There are none of them are capital R's. Your radii are 10 to 30, those are your constants.
So it
Okay. I think y'all are coming up with a new integration technique. I don't know that well. Are you counting this as this is a constant and that's going to be r squared over 2 then? I'm not sure that's legal in most states. Second? Distribute the r into a radical. I guess you could, as long as that was r squared that you're distributing in there. Possibly. Now, because this is in the numerator and that's in the denominator, I don't know that math either. Okay. I'm having trouble with it. How would you do it? I go like that.
Keep the same thing, but then it'll be to the 2/3 of it.
Oh, we're going to treat this as a constant and have that as a variable. Right? I'm not sure I know how to do that well either. Oh my goodness, why don't we try the substitution? What might we substitute? Let u equal 1 plus r squared. I kind of like that. I can understand that one. Y'all aren't doing this high-level math on me now. Okay, what's the next thing we do? Then du is equal to 2r dr, right? Okay, well, I have an RDR there, but I don't have a 2RDR, so what might we want to do? Divide by 2, okay? So that'll get rid of that. So now I've got my RDR there. That's pretty good. And I can do this other thing there. I think we're okay, maybe. So if I'm dividing by 2, then that's probably going to make that a 15, isn't it? Okay. And then your integral will be, what do we do with that 10? Maybe 101? Okay, yeah, we'll do the plus there, okay? What is the again?
It says 1600.
Okay. 901. Okay. 30 squared is 900 plus 1. Okay. All right, then what do we have? The RDR becomes your du, because we already took out the 1/2. What's the next part? What is 1 plus r squared? U, okay. U to the negative 1/2. Okay. So this will be 15 pi times, I don't need that. We're going to integrate, so we don't need to do another integral sign. What's the antiderivative of u to the minus 1/2? Okay. I couldn't understand. 1/2. Okay. Negative 1/2 plus 1. Plus 2/2. Okay, it's 1/2. What will we also need? A 2 here. Okay. And that's evaluated from 101 to 901. Think we're going 901. Okay. Think we're going to need a calculator on this one. But what we're saying I'm going to do is take that 2 out here and make it back to a 30 again, just for funsies. So that would be 30 pi, and then it's basically the square root of 901 minus the square root of 101. Okay? I'll give you an approximate answer then. 30 minus 10 would be 20, so that'll be something a little bit greater than 600 pi. But I think you can do better than that if you actually do the calculation. It'll be actually, yeah. So 1881? Is that what you said? Okay. 1881. But this, remember, your population density was thousands. If you go back and read it, thousands per square kilometer. So this would be thousands. So this would be approximately 1.9 million. Okay. Just around it because really only had like two significant digits anywhere, so 1.9 million would be close enough. Million people live in that circle. Okay. Just because we're not in chapter 5 anymore, we can still use substitution. Okay. It's not forbidden. That was just not just a chapter 5 issue. Okay. Very good. Just for funsies, tell me what 600 pi came to. Is that what you did, or did you do the square roots? What? You actually did this, didn't you? Right. Tell me what 600 pi would have been. Do you have a pi key on the calculator? 1,884. Okay, so that was still around that 1.9 million. Yeah, I figured that was going to be awfully close. Okay. All right, unfortunately, just when we're having fun, but we always have fun, okay? We'll start next time with flow rate, okay? We started this time in 6.2.1, so we did the 6.2. Let me give you a few homework exercises here. Let me get something to mark my place. You can do number 1 or 3 or 5. Whoa. Let's do any of the odds 1 through 7, okay? And I would definitely do some of those because sometimes they give you figures and sometimes they don't, okay? But even when they do, they don't tell you what to do with them very much. So try any of those odds 1 through 7. Then do any of the odds 9 through 13, and they give you no figures there, so definitely do some of those. Then do some of the odds 15 through, wow, (15 through 33). Some of the odds 15 through 33. I stopped there because the next part is doing the flow rate, and we haven't done that yet. Good deal. All right, good deal. Hope you feel better. Yeah. Is it getting better?
Yeah, last night I woke up, I couldn't breathe no more. I guess I was walking up too much. So I took like 3 different types of medicines. So I took NyQuil, I took some Enzyme C, and this other like MSA ID.
You didn't overdo it, did you?
Probably. I woke up this morning. I was feeling like I got rid of my truck.
Yeah.
So,
Well, part of that was the cold, and part of it was probably a little bit of more medicine than you probably needed. Because I don't know how you're existing. Because if I take one of those, unless I take it right at the beginning of the night, I am miserable the next day. So yeah, hung in there well today though.
Monday to go back home before I go to work. Get some medicine.
Alrighty, good deal.
Also, business statistics. Is that
What's that?
business statistics. Is that harder than calculus or
What did you say?
business statistics?
Oh, business statistics. I would say no. It's a different language though. With statistics, you're talking about deviations, variance. You're talking about populations, dealing with probabilities and probability functions. So it's a whole different language, but technically I think it's easier than calculus. Of course, knowing calculus areas on the curves should make statistics make a lot more sense. But a lot of times they don't teach it from that. They just say use the tables, and you don't know why you're using the tables. So are you having to take that at some point?
Yeah, because I might take it. Because I'm trying to, I might get major. I'm my master's in business.
What's that?
I might get my master's in business.
Oh, I see.
So civil.
What's your major now?
I'm still civil engineer.
Civil engineer. Yeah, that's right. Both of them. All right, good deal. We'll see you Wednesday. Hey, we've decided to have class 2 days this week. How's that? Okay. Nice, huh?
Okay. Take care.